All right, welcome everyone. I'm Neil Fortner. I'm the Chief HDF5 Software Architect at the HDF Group. Today we're going to be talking about two new features in HDF5 that were developed under the Exascale Computing Project, Subfiling and Multi-Dataset. Up first is Subfiling, and Jordan Henderson is going to be talking about that. So take it away, Jordan.
Yeah, hi everyone. I'm Jordan Henderson. I'm a software engineer at the HDF Group. And today I just wanted to talk a little bit about the Subfiling VFD, which is a new file driver for HDF5 that's been in development recently. Next slide. So just a quick recap, HDF5 virtual file drivers are pieces of software that let users define the mapping between the HDF5 address space and the underlying storage that the HDF5 file gets written out on. So for example, the Sec2 VFD just uses POSIX.io to write out the bytes of the file. The core VFD operates directly in memory. The multi and family VFDs split up the HDF5 files, data and metadata into different files, and so on. And you use these virtual file drivers by setting them on an HDF5 file access property list with the generic H5P set driver call, or by a specialized call that the driver itself might expose. Next slide. So here's a quick overview of the current architecture for the HDF5 library. And in red is the general part of the library that we're interested in this talk, the VFD layer. And you can see some of the drivers that I just talked about there, including the new subfiling one. Next slide. So let's go ahead and talk about the subfiling VFD a little bit. So as for availability and requirements for it, an initial version of the VFD was released in the 1.13.2 release, but then there was some further development on it after the point that was merged to the develop branch for the 1.13.3 and upcoming 1.14.0 releases. So for requirements for it, you have to build HDF5 with parallel support, and you also have to turn on the subfiling VFD because we don't build it by default since it's not completely supported across all the platforms and compilers that we currently support for HDF5. You have to have a C11 capable compiler because it uses some of the C11 atomics. And then the HDF5 application has to call MPI init thread, and the MPI implementation has to be able to support the MPI thread multiple level of threading support. Next slide. So what is the VFD? It's an MPI-based parallel file driver that allows the HDF5 application to distribute the HDF5 file across a collection of subfiles according to equal size data stripes. So the stripe size you pick for these data stripes is the amount of data that you can write to a particular subfile before the data gets placed in the next subfile in round robin fashion. So it's kind of like Lustre striping in a way, but it's more like a software rate 0 implementation. And by default, we use one subfile per machine node and use 32 megabyte data stripes. So the goal with the subfiling VFD is to kind of try and find a middle ground between the single shared file and file per process approaches to parallel IO as HDF5 applications kind of scale up into exascale territory. And so we want to try and minimize the locking issues for the single shared file approach. And we want to try and reduce some of the complexity and the total number of files that get generated compared to the file per process approach. And we designed the VFD to be a little more flexible and configurable because we assume that getting the optimal performance is a machine-specific kind of thing. And so we want to allow you to be able to configure it as you need for a different machine. Next slide. And so the VFD uses a system of what we call IO concentrators. And these are just a subset of the available MPI ranks in the application that control these subfiles and have thread pools that do IO on them. So there's an N-to-1 mapping from the subfiles to the IO concentrator rank. So one particular IO concentrator can control more than one subfile. And the subfiles are just round robin across these IO concentrator ranks according to how the application chooses to select the MPI ranks as IO concentrators. And then IO from the different MPI ranks is forwarded to the appropriate IO concentrator based on the offset in the logical HDF5 file that they're doing IO on. And so the VFD outputs several different files for a logical HDF5 file. There's this stub file, which looks like just a regular HDF5 file. There's a configuration file that it outputs and uses, and then there's all the subfiles it creates, which is shown in this little picture to the right. Next slide. So the current architecture of the VFD is that the subfiling VFD is stacked on top of an IO concentrator VFD on every MPI rank. And the subfiling VFD manages the information around subfiling. So the data stripe size, the number of subfiles, and so on. And it also breaks down IO requests into offset and length vectors based on your stripe size and where in the file the IO is going to. And then the IO concentrator VFD just receives those IO vectors and then queues up IO calls to the right IO concentrator rank. And then, of course, there's the subset of MPI ranks that get selected as IO concentrators. They control one or more subfiles, and they receive these IO calls, translate them into the right file offsets for the subfile they're controlling, and then they relay the IO to it. Next slide. And here's just a quick little diagram of what that looks like. And you can see the subfiling VFD on top of the IO concentrator VFD on each MPI rank. And then they can all talk to any of the IO concentrators, which just use POSIX IO calls to write to the file on node local storage, parallel file system, or any other type of file system that the file might be on. Next slide. So I'll talk a little bit about the components of the VFD and the files that it outputs. One is the HDF5 stub file, which looks like a normal HDF5 file, but it just has the HDF5 superblock information and the subfiling parameters. This stub file is mostly useful for legacy kind of HDF5 applications where they read the initial bytes of the file to try and figure out what it is. So for example, CGNS and NetCDF4 do this. And then we use the inode value of this stub file to get unique file names for the other files that we're outputting, the configuration file and the subfiles. Next slide. So then there's the configuration file that gets output, and the subfiling VFD just creates and uses this so that it can figure out what subfiling parameters were used for an existing file when it's opening it. And then once it's opened, it validates it against the information it has stored internally. And this configuration file is mostly useful for external tooling to be able to figure out the parameters that were used for subfiling. And so this picture here is just a quick example of what the configuration file might look like. Next slide. And then, of course, there's the subfiles that get output, and these just contain all of the data for the file, including the superblock information that gets duplicated in the stub file. And these subfiles currently get placed right alongside the stub file and the configuration file, but future development might allow you to put them somewhere else. So that way, maybe you could have the stub file and the configuration file in your home directory on a machine, and you could put all the subfiles on a bigger capacity parallel file system. And so there's two ways that you can get the data out of these subfiles. The first, of course, is to use the subfiling VFD, and you can just simply read back the data. But you can also stitch all of these subfiles back together, and that will just give you back an ordinary HDF5 file that you can read with HDF5. Next slide. So here's some of the new API calls that get added with the subfiling VFD. The first one, this H5P set FAPL subfiling, just modifies the file access property list you give it to use the subfiling VFD. And then you pass in a subfiling config T structure, and that has all the subfiling parameters that you want to set up the VFD with. And you can also just pass in null, and we use default values in that case. And then there's the H5P get FAPL subfiling, which just returns the subfiling parameters that you set on the file access property list, or it'll give you back default values if you didn't set anything. Next slide. So here's what the configuration structure for the VFD looks like. The first few fields in it are pretty boring. The magic and version fields just have to be set to these predefined constants. And then the IOC FAPL is a file access property list that's used for the IO concentrator VFD. And this require IOC field always has to be set to true. But the last field, the shared config, is the more interesting part. It's where you set the actual subfiling parameters. So there's this IOC selection field, and that's how you can tell the subfiling VFD the way to select MPI ranks as IO concentrators. And then there's the stripe size, which is the size in bytes of the data stripes, and then the stripe count, which is the target number of subfiles that you want to use. The next slide. And here's quickly that IOC selection field. By default, we just select one rank as an IO concentrator for each node on the machine. But we have a couple of other methods, like every nth rank, where you start at rank 0 and then you skip a certain amount when you choose the next one. This with config one isn't implemented yet, but we've left it in for now. And there's this total one where you just give it the total number of IO concentrators that you want to use. Next slide. Here's a quick example. The link up above is a more full example of how to use a subfiling VFD, but basically the way to use this in an HDF5 application, you first set the MPI parameters that you want to use on the file access property list, since this is a parallel VFD. And then the easiest way is to call the get FAPL subfiling to grab a default configuration, and then you can adjust it as you need and set subfiling on the file access property list using H5P set FAPL subfiling, and then you create your file with the file access property list. Next slide. And this was an example I wanted to show, since this is pretty common, but if your HDF5 application wants to pre-create your file on just rank 0, then rank 0 needs to know ahead of time how many subfiles that you want to create. So this is pretty similar to the last example, but the difference here, you can see that in the subfiling configuration, I specifically set to use 20 subfiles. And so when you pre-create the file on rank 0, it'll go ahead and create all those subfiles, and then you can go ahead and open the HDF5 file on all the ranks you have in the application, and everything will be set up correctly. Next slide. And then I wanted to go ahead and mention this H5 fuse script that we created. Here's a link to what it looks like. And all it does is reads the configuration file that the VFD created, and then it uses the information there to stitch all the subfiles back using DD, and it results in just a single HDF5 file that you can read with HDF5 as normal. And so when you build the subfiling VFD, the script will be installed under the bin directory of your installation as h5fuse.sh. And here I just showed a little example of kind of what it looks like while it's stepping through the subfiles and stitching them back together. Next slide. And so quickly, I just want to talk a little bit about some of the initial performance results that we gathered. So one of the first applications that we tested subfiling with is CGNS, which, for those that don't know, is a computational fluid dynamics notation system. And so we used a slightly modified version of CGNS, which just has the calls needed to set up subfiling. And we ran this benchmark HDF5 program, which writes and reads mesh coordinates, the element connectivity, and solution data. And we ran it on Summit, which uses GPFS for its parallel file system. And we used a mesh of 130 million elements. And so you can see here, as we scale up the number of MPI ranks by doubling them, we double the file size that results. Next slide. And so here you can see we're comparing the CGNS time for native HDF5 using the MPI IO driver. And this is the MPI IO driver is using independent IO, which we don't expect to scale particularly well, especially as we get up into 20,000 plus ranks. But you can see here that subfiling remains pretty constant and scales pretty well as you scale up the number of ranks. Next slide. And so here's some additional results that we got from running IOR on Summit, and we used a modified version as well, where we just added in the subfiling calls to set it up. And so you can see here that collective IO with HDF5 doesn't really scale that well as you scale up the number of MPI ranks. The numbers here for subfiling should be noted that they're artificially high because they didn't really take into account system-wide file caching. But the thing we mostly wanted to focus on is you can see how we can still get better performance as compared to collective IO, even though there's definitely caching in place here. Next slide. And so finally, just some more information and documentation here. There's a link here to the original subfiling VFD RFC. It's a little bit out of date now, but it contains some good information about the concept and some of the things that we thought about when designing and implementing the VFD. And then there's also this link here to the current documentation for subfiling VFD that we've generated with Doxygen and are hosting online. So next slide. I think that's about all I have for the VFD. If there's any questions or comments, I'd love to hear them. I can see Marta has her hand raised.
Yes, if it's okay, I have some questions.
Sure.
So first, does it work, and excuse my ignorance, would it work with Deos?
We haven't used it with Deos yet. Of course, anything's probably possible, but Deos definitely wasn't a target that we had in mind for it.
But is potentially it will be maybe a future test that could be done? I mean, as of now, by default, is there anything that could be a road blocker? It's just that maybe there was not enough time to test it, but is there any feature in the design that you could say as of now, it will not work?
I wouldn't say a road blocker. It's definitely more of an architectural thing. Like I say, when we designed and implemented the VFD, we never really considered Deos. So there would be a pretty big architectural overhaul to get it to work with Deos. But again, I'd say just about anything is possible, especially at the VFD layer with HDF5. So it could be doable.
Are you thinking of Deos as in the Deos HDF5 connector, the vol connector, or the standard HDF5 with DFS?
The one that will be on Aurora. I don't know which one. On Aurora, the X-Scale at Argonne.
Right. Yeah, I don't know what they're planning to do. Does anyone else know? Okay,
maybe it's a follow-up discussion. Another question is in your test with on Summit. How much was required to restructure the code? Was it your IO test or the other case, CGNS? Did you have to change completely the way the IO was done to get those results, or was it a relatively easy modification?
Nope. It was, we didn't change anything about the IO patterns. We just simply added the calls to use the subfiling VFD instead of HDF5's typical MPI IO driver.
Okay, great. And eventually, how do you decide how many IO, what is the IO connectors? This is a parameter that you enter, right? How do you decide that number? Is based.
So, Lori, can you go back just a little bit where I show the example of how to use it in the gray boxes? So one way that you can choose how the number of IO concentrators you want to use, you can specify here in the VFD configuration structure. But there's also environment variables that are listed in the documentation link I posted at the end. And you can set a configurable number. You can set anywhere from 1 IO concentrator per node up to 1 for each rank on the node. And so, of course, if you use 1 for each rank on the node, it's basically equivalent to doing a file per process approach. But yes, it's very configurable. And typically from different machines, we found that using 1 IO concentrator per node gives generally the best results. There have been a couple of machines where using 2 per node has done a little bit better, but in general, the idea is by using just 1 per node, you kind of reduce the number of subfiles that get generated compared to file per process. So it just kind of makes things a little bit easier than having 1 file per process.
And is that, do you think, something that could be pre-processed generically for everybody using the same machine, or do you see maybe that to be specific to the application mainly?
Yeah, so that's kind of why we wanted it to be a little more configurable, because we assume that depending on the machine, you know, maybe 1 per node may not give the best results, and so subfiling is fairly configurable in terms of how big the subfiles are, how many subfiles there are, and how many IO concentrators you use. So there may be a little bit of experimentation for different machines, but at least so far we found that 1 IO concentrator per node works pretty well on most machines.
Yeah, we didn't mention it, that you can set some of these parameters through environment variables. So if you find, for example, on a machine that 2 is always the best for an IO concentrator, you can always have a global environment variable set. So that would be the default for all the users, if that's what your goal would be.
Yes, at least, yeah, because when you, so is there going to be a default when you install HDF5 with a version that allows to do this, or is the user who should enter a value? Like by default, there is null and that you have to enter.
Right. So the default is 1 per node in terms of IO concentrators, and then the user, if they want to, they can adjust that.
Okay, thank you. And your last question, your graphs, the ones that you present, the results of IOR and CGNS, are they with the best option? So did you try to get the best results, or is just an example of how much can we get with a normal evaluation?
I think maybe Scott might be better to talk to that, but I think in general, we just we used the set alignment call in HDF5 to align IO along with like the parallel file system stripe size. So we did a little bit of adjustment for good results, but we did whatever we did for subfiling, we did for the MPI IO driver as well.
Yeah, we tuned both CGNS and IOR. We try to tune it as best possible with a single shared file. And we have another result for, this didn't show up. We have the CGNS run with collective, so we can compare. So collectives is worse in this case for CGNS, so it's not shown here. But so we tried to tune the single shared file so we can get a good comparison.
Thank you so much.
We have a few more questions in the chat, but we might answer quickly and then move on to the other topic, and then more questions at the end.
Yeah, I can go ahead and answer Wei King's question real quick. The original design for the subfiling VFD was supposed to allow the IO concentrators to use any sort of VFD they wanted for writing the data out. So, you know, theoretically, you could use HDF5's MPI IO VFD, but the problem with that was that the VFD layer isn't thread safe, and the IO concentrators use an IO thread pool. So for now, we just use direct POSIX P-read and P-write to write out the data. But that might be some future development work, is making the VFD layer thread safe, and then you could use whatever VFD you wanted underneath. And that's why in the subfiling configuration structure, there's the FAPL ID parameter for the IOC VFD. So you'd be able to set up whatever VFD you wanted on it. And then for your other question for the round robin strategy, yeah, so the data always starts at subfile 0, and then we just round robin the data in segments of the data stripe size. And when you get to the last subfile, it just round robins back to subfile 0 again.
Okay, thanks, Jordan. I think this is great talk. Just another comment about round robin strategy. Does the round robin strategy apply for individual data set, or is applied to all the data set? Meaning, if I want to round robin assign one data set, I always start with the subfile 0. And if I have hundreds of data set to write, and apparently subfile 0 will get more data than other subfile, right?
It would depend on how much data you're writing. So, you know, if you pick a 32 megabyte stripe size, for example, then the first 32 megabytes of the HDF5 file are in subfile 0, and the next 32 are in the next subfile, and so on. So you can kind of pick your stripe size to distribute the data sets how you want, if you know how big they're going to be. But the round robining of data is just the bytes of the HDF5 file. So it's not exactly working on the data set level, but just the byte level.
I see. Thanks.
Okay, so I guess if there's any more questions, if you ask them in chat, I'll answer them. But I think I can hand it over to Neil to talk about the new multi-data set feature.
All right, thanks, Jordan. While I get set up, I want to mention quickly, I forgot to say that we're recording the meeting, and we'll have the recording posted after the meeting. All right, so now I'm going to talk about the multi-dataset IO feature that was developed under the same project. This has actually been in development for a very long time, but it's finally we're finally about to merge it in right now. So a quick review of how HDF5 stores data. So you probably know that data in HDF5 is stored in the file in datasets, which are arrays of binary data. And HDF5 can consist of any number of data sets, which can describe things like different variables like pressure, temperature, velocity, whatever. Right now, the way you read and write data to these data sets is via H5D read and H5D write, which only operate on one data set at a time. So if you have if you have a time step and you have to write out 50 different parameters that are in 50 different data sets, and you need to make 50 different calls to H5D write. And data sets can additionally be broken up into multiple chunks, which are sort of logical delineations, like tiled blocks in the data set. And each of these chunks are stored separately in a contiguous block in the file. And you can also perform IO on just a selection of the data set, just a subset. So you could select only one column or only a certain block inside the data set or something like that. You don't have to read and write the whole thing at a time. So that would not be convenient. So right now we have MPI-IO parallel IO for data sets. And we've had this feature for a while, but there are several different, there are multiple ways that this is actually performed. So the default method is independent IO, which is basically every rank. So if multiple ranks are doing a write, then every rank just kind of does it at their own speed, and there's no coordination between any ranks. And so this has the advantage that you're not waiting for other processes to catch up before you can do your IO. But downsides are you can't, since we can't call MPI file set view because that's a collective operation, and with an independent operation, we don't know that all processes are participating. That means that we can't describe a non-contiguous IO block. So we have to do if the IO is doesn't map to a single contiguous block on disk, then we need to make multiple calls to the underlying MPI file read or write. And in addition to that, we're can lose performance because we're not giving MPI the full picture of the IO, both because we can only send one contiguous block at a time, and because we're not giving MPIO information from all the ranks. So as a quick visual example, so say you have this a chunked data set with 4 chunks here, and each chunk is 5 by 10 elements, and you're selecting the first 3 columns in each chunk, or the first 3 columns in the data set and columns 10 through 12 in the data set. So if you want to make this call with say this is just rank 0, so we're only looking at one rank right now, but you can kind of apply it to multiple ranks. So it just rank 0, try and make this simple selection. It needs, since the only contiguous blocks are these 3 elements at a time, it means that it's from one HOD write call. It needs to make, the file driver needs to make 20 calls to MPI file read or write. So you can see how that could be inefficient, because we're not telling MPI what we need to do. We're only telling MPI a small piece of what we need to do at a time. And going to one step more higher level of information, we have the multi-chunk collective IO, and this is where HDF5 looks at each chunk in the IO request, and at each chunk it will issue a single MPI file read or write for that chunk. And the underlying IO can be either independent or collective, but it's still collective at the high level. So this requires that all these other than independent, all the other methods I'm going to talk about require that all processes call the HOD read or HOD write collectively. And so this gives more information to MPI than independent. So it lets you know the IO parent for the entire chunk, but it doesn't let you know the IO parent for all chunks. It's only one chunk at a time. So instead of one block at a time, it's one chunk at a time. So with the same example, so instead of doing a call for each set of 3, you create an MPI data type that describes this selection of 3 columns within this chunk. Then you make a MPI file read or write for that call. Then you move on to the next chunk and do the same thing. So you make 4 calls total instead of 20 in this example. And then, so in the highest level of IO information in the current library is called linked chunk collective, and this is actually in most cases the default if you're doing collective IO. And this is where the library builds an MPI data type that spans all the chunks in the IO. So it takes into account the offset of each chunk in the file, and then it offsets sub MPI data types in a struct. A struct, sort of a meta MPI data type struct. And so similarly, the IO can be independent or collective, and for each data set, you only make a single call to MPI file read write. And this gives the maximum amount of possible information possible to MPI given the current HDF5 API. So go back to the same example. In this case, it builds an MPI data type for this selection, an MPI data type for this selection, MPI data type for this selection, this chunk, an MPI data type for this selection, and then it stitches those 4 data types together into a single giant data type that describes all 4 at once. And so it only needs to make a single MPI file read or write call. And so what we have just developed and is under final review right now is called multi-dataset IO. And this is a new API along with new underlying algorithms that allows the application to perform IO on multiple data sets at once. So again, the current API requires that you make a single API call per data set, but now you can, with this new API, you can make a single API call to read or write to multiple data sets. And then the underlying library will, similar to linked chunk, it'll create an MPI data type that spans all the chunks or contiguous blocks in all data sets. So you can make, even bigger MPI data types that give even more information to MPI. And so we have right now it's in the features multi-dataset branch, and it will be merged soon and available in 1.13.3, which is the next 1.13 release. So here's the API real quick. So it's very similar to HID read and HID write, except you have these this count parameter at the start, which is h size t, and that's just the number of data sets. And then after that, all the parameters are the same, except they've been turned into arrays, except for the dataset transfer property list, which is still static. There's still only one DXPL. Other than that, all the other parameters are all arrays, and all the arrays have a length of count. So we did some quick benchmarking. We haven't done a whole lot, but so here's on Summit we ran. So on the right is independent. So as you would expect, there's not much difference because, obviously if you call multi-dataset independent, it can't really do anything different. It's still going to have to do each contiguous block one at a time. So you can kind of see that there, that the lines track each other. But so for collective is a more interesting case. So you can see here, especially for the right without multi-dataset, this is a time. So bigger numbers are bad here. So it really has trouble scaling here. It goes up to 600 seconds, where when you use multi-dataset, then it's about 40 or so at the high end, and it's much lower, at every number of data sets. So this benchmark is interesting in that it has a constant number of ranks, and it only varies the number of data sets. And it's a constant amount of data per data set. So as you go to higher data sets, and it's more data being written. And so here we show a much great improvement for write, but it actually is, once you get at low number of data sets, we also see an improvement for read, but at higher numbers of data sets, then the read gets a little slower. And we're not sure exactly why. We haven't really, this is pretty new, but it could be, that MPI is just, the data type is getting too big. So, we think, obviously this can give you a huge performance boost, but, you want to check and make sure that it's actually the best for your case, because in some cases it'll help, and in some cases it won't. Just like independent versus collective. In some cases, collective makes it much faster. In some cases, it makes it much slower, as you'll see in the next slide, where again, if you look at just collective results on Polaris, we actually see that substantial, but not as dramatic as the last time, but substantial improvement for multi-dataset for both read and write. But the thing to keep in mind is, again, you see that there's basically no difference in independent, but the independent on Polaris, for some reason, is much faster than collective. So again, you want to look at your use case and your system and make sure that you're using the fastest settings, because there can be pretty major differences in performance depending on what settings you use and depending on what system you're using. And we had another quick benchmark, which uses a much smaller number of data sets. And this was just kind of a quick modification of an existing CGNS benchmark, similar to what Jordan talked about. And so it only went from 16 calls to 6 calls, so we don't expect a huge improvement, but we did see 6 to 10% improvement with using multi-data set instead of single data set. All right, so in quick, I'm going to go over what cases are supported and what cases aren't. So, so in order for it to work, then all ranks need to pass the exact same list of data sets. If you're calling it in collective mode, we thought about not having this requirement, but it ended up being very difficult and would have required extra coordination that we would have to do every time. So we thought it was best to just require everyone to pass the same list of data sets. And of course, ranks can select 0 bytes in data sets they're not interested in. And all the data sets in the operation need to be in the same file. We can't do, construct an MPI data type that crosses files. And each data set may only be present once in the list. And that's mostly because it would be very difficult to construct an MPI file data type that had monotonically non-decreasing offsets in the general case if we allowed each data set to be present more than once. And it's also worth mentioning that the selection IO feature is fully supported. That's a different feature that's also, it's new and somewhat experimental, but it basically allows the library to pass data space selections to the virtual file driver instead of one offset length at a time. That allows the VFDs other than MPIO to get the advantage of having more information about the IO, the full IO request. But for now, we're concentrating on the MPIO VFD for this presentation. And so all these first three things are necessary in order to not have errors. And then if you want to have, then after that, then anything will work that also works in regular HDF5. But if you want to get a benefit and get the sort of the simultaneous multi-dataset IO, the sort of mated linked chunk IO that I mentioned earlier, there are a few other requirements. So obviously you need to be in collective mode. None of the data sets can have data filters or compression, right? We haven't written a special algorithm for multi-data set with compression yet. And none of the data sets can have type conversion. That's a pre-existing requirement for collective IO to be handled in a collective manner. And we haven't implemented a collective type conversion yet. And all the data sets need to be contiguous or chunked, so no external or compact or virtual data sets. And if you don't meet these 4 requirements in the subheadings, it'll still work, but it will instead process one data set at a time. So it won't be any faster than if you just called HFD read in a loop or something like that. But it may be more convenient. And so so the current status is, again, it's in a feature branch and it's under final review and should be merged soon. We've also updated the vol or the virtual object layer, and we basically changed the read and write callbacks to always be multi-data set. So that this means that if you're writing a vol connector, that it's going to need to be updated for the new read and write callbacks, along with some other changes that we made in 1.13. And we still support multi-chunk and independent IO, but we don't support linked chunk one data set at a time, because we figure that if people want linked chunk, they probably, and they call multi-data set, they probably want just the linked data set IO, the fully collective IO path. But if there's a demand for it, we could reinstate it. It wouldn't be that hard. We just have to basically copy the code and make a few changes. And if it's worth keeping in mind that if there are any data sets and lists that don't meet all these requirements, so if most of your data sets meet all these requirements and one of them has type conversion or something, then that's going to break the simultaneous multi-data set IO for all the data sets, and they'll fall back to multi-chunk. So if you want to use the simultaneous multi-data set IO, you want to make sure that if you do have type conversion, that you put that data set in a separate call. And we're planning to, in the future, implement support for type conversion with collective IO and multi-data set. So that would give you, all these benefits with being able to use type conversion. So does anyone have any questions?
Thanks, Neil. I have a question about the limitation in the official release of 1.13.3 or 1.14.0. So the limitation you mentioned here, are they applied to 1.13.0 or it will also apply to 114, some 113.3 and 114.0?
I am not sure exactly when we're planning to release 114. Dana, do you know?
Yes, 114 is probably going to be released. My target, what I have written down the official schedule is December, but I'm gonna try to squeeze it out before Thanksgiving.
Right. Yeah. So no, it'll be a limitation 114.0 as well.
Okay.
And I get dataset collective type conversion in before then.
Oh, and that would be great. Thanks.
Any other questions?
As always, feel free to post on the forum. The people presenting here and others from the HDF group, keep an eye on the forum and would be able to answer your questions. And I will process this video pretty quickly and get the video and the PowerPoints up on our website and on the forum for you guys to review.
I do have a last minute question.
Sure.
For these subfiling and multi-data set features, is there any plan to make it available to Python program?
So we don't develop H5Py, but I would assume that the H5Py developer is going to add Python APIs for these.
All right, thanks.
Yep.
Okay. If that's everything, we'll go ahead and end this. And again, feel free to continue the conversation on our forum at forum.hdfgroup.org. And let's see. Okay, so Thomas Cliver happens to be on the call, and he's one of the developers for H5Py. In the chat, he said it'll probably be a case of PRs welcome, unless one of the maintainers is eager to use those features. So, and we also host a little forum for H5Py within ours. So if you poke around, you can find that under, I think, ancillary tools. All right, everyone, thank you very much. I'll try to get this posted this afternoon, and have a good weekend.
Thanks, Lauren.
Thank you.